Okay, we're going to finish up this part 4 with starting with problem number 52. And with problem number 52, we start talking about the interaction between two vectors at the same time. The first problem number 52, Brian Allen pedaled a human-powered aircraft across the English Channel from the cliffs of Dover to Cape Grisnez, June 12, 1979. He flew for 169 minutes at an average velocity of 3.53 meters per second in a direction 45 degrees south of east. What is the displacement? Okay, the displacement is going to be the same as the distance in this case. We have 169 minutes. I chose to change that to seconds by multiplying by 60, and you get 10,140 seconds. And the displacement is going to equal his average velocity, which was 3.53 times that 10,140 seconds. So you end up with 3.58 times 10 to the fourth meters. And in order to make that a displacement, you just have to put in the direction, which is 45 degrees south of east. B states that he has a headwind of 2 meters per second, which is in the opposite direction. So what is his velocity relative to the air? Well, the air is going this way at 2 meters per second, and he's going this way relative to the earth at 3.53, since that would mean that he would have to be actually going 3.53 plus 2, or 5.53 meters per second in a 45 degree south of east direction relative to the air. And then the last question is, what is his displacement relative to the air? Well, we would use this velocity instead of this velocity with the same time. So 5.53 times 10,140 would be a displacement of a displacement of 5.61 times 10 to the fourth meters, again 45 degrees south of east. Number 56. Now, number 56 is actually a very interesting problem and could appear on a quiz or test. This takes the same problem we did in number 38 and then adds the fact that we're going to, instead of looking at in relation to the ground, which is what we did before, we're going to look at in relation to the quarterback. This is the vector for his velocity of the ball in relation to the ground right here. We'll call that V0, okay? We know that V0 is 15.2 meters per second by our calculation, and we know the angle is 25 degrees. We also know that we'll call this VA, and we know that is minus 2.0 meters per second. And we also know that there's no angle there. That's only an x component. And what we want to find out is, what is this vector, which is the velocity vector relative to the quarterback, which means we have to find this magnitude of this velocity plus the new direction that will result in this once we've added this vector and this vector together. So VA plus V0 is going to equal V, and we'll call this VB. This will be VB right here. So that means that VAX plus V0X equals VBX, and VAY plus V0Y is equal to VBY. Now we'll do the Y first because VA has no Y component. We can mark that out right away. And so that means that V0y is equal to VBy. We know V0 is 15.2, and the y component of that is going to be the sine, if we multiply this by the sine of theta, and that's going to give us VBy. So if we do the math on this one, VBy is 6.42 meters per second, and that's VBy. Now VBx is a little more complicated. We know this is minus 2 plus whatever V0x is going to be equal to VBx. So minus 2 plus 15.2 cosine 25 degrees equals VBx. Now the reason I stopped there is that this actually, because this is in the opposite direction, this should be a sum here. And so you end up with, when you do the math here, 15.8 x. So VB is going to equal the square root of 15.8 squared plus 6.42 squared. And so VB is equal to 17.1. And the angle is going to equal the inverse tangent of 6.42 divided by 15.8. And the angle, therefore, is going to be 22.1 degrees. And I'm not quite sure how I got the signs messed up here, but I know that this has to be added to this in order to get to VBx, because obviously the x component of VB is bigger than V0. So I'm not sure where I made the mistake on the sign there. So that's the angle. The next problem is problem number 61. A sandal is dropped from the top of a 15-meter high mast of a ship moving 1.75 meters per second due south. So it's traveling 1.75 meters per second, and it's dropped from the top of a 15-meter mast. Calculate the velocity of the sandal when it hits the deck of the ship relative to the ship, relative to a stationary observer. Well, relative to the ship, it's going to be traveling straight down. And so it's only going to have, because it has a y component, the way I've it's going to have a y component of 1.75, which it will still have when it hits the deck of the ship. So it's into the ground component, we'll call that x, or z. That into the ground component is going to be determined by this equation. Vz is equal to vz squared is equal to vz0 squared minus 2 times AD, or GD. And so that means that Vz is equal to the square root of Vz0 squared minus 2 times minus 9.8 times 15, which is the height from the deck. And it wasn't thrown toward the deck, and so this x is out, and the two minus signs cancel each other out. So into the deck of the ship, it's going 17.1 meters per second. It has no other components, so relative to the ship, it's going straight down into the ship at 17.1 meters per second. Now, the second question is relative to a person on the shore, in which case it's going to have a z component of 17.1 and a y component of 1.75 meters per second. Those will be the two components. And So the V is going to equal the square root of 1.75 squared plus 17.1 squared. And so that's going to equal 17.2 meters per second. And then the angle that it goes is going to be tan minus 1 of Vz over Vy, which is going to be 17.1 over 1.75, tan minus 1 of that. So the angle is going to equal 84.2 degrees. But what that means is it's going this way and down into the thing, and I can't draw it in 3 dimensions, but it has that kind of 3-dimensional look to it. Number 65 is the last problem, and it talks about a swimmer. And so let me read exactly how the problem is stated. An athlete crosses a 25-meter wide river. He's swimming perpendicular to the current, and his speed is 0.5 meters per second. So that's how fast he's swimming. He reaches the opposite side at a distance 40 meters downstream. So he's down here. How fast is the water in the river flowing with respect to the ground? So in other words, if he swims, how fast is this water flowing in this direction in order to propel him 40 meters downstream? Well, we know for him to get across the river that y is 25, and it's going to equal his y velocity times the time it takes him to cross. So the time it takes him to cross is going to be y divided by vy, which is going to be 25 divided by 0.5, which equals 50 seconds. So it takes him 50 seconds to swim across. We also know that in that 50 seconds, he's propelled. So in that 50 seconds, he's actually propelled downstream 40 meters. So 40 meters is equal to some number times 50 seconds. And so the current has to be 0.80 meters per second. So the current's 0.80 meters per second. It says what is the speed with respect to the ground. So his speed is actually going to be the combination of this y component and this x component. So his actual speed or velocity is going to equal the square root of 0.5 squared plus 0.8 squared. And if you do that math, you get 0.9 meters per second, and the angle is going to be the inverse tangent of 0.8 divided by 0.5. So his angle is going to be 58 degrees downstream from directly from the perpendicular. So this angle right here is 58 degrees. And that completes this last part